My name is Parkit Kulanath Pochen.
Hello everyone, my name is Thitirat Somsuphangsi. Our project is NROC, which actually corn spelled backwards. Modern sweet corn farming requires precise environmental tracking to yield high-grade crops. The core challenge is that farmers often struggle to correlate environmental data like temperature and humidity with the right harvest window. This gap between data and decision is what motivated our project. Our project works with two types of data, time series sensor data collected from the field and external API data from the weather forecast service. The objective is to explore, pre-process, and analyze and evaluate this data to understand environmental conditions and support smarter agriculture decision making. So what exactly are we predicting? The core question is, in the next 7 days, what growth state will the sweet corn reach? And by extension, will it be ready for harvest within 1 week? Now you might wonder, if OpenMeteor already gives us a temperature forecast, why do we need a model at all? The answer is that OpenMeteor measures air temperature 2 meters above the ground at a general weather station, but what actually drives corn growth is the temperature inside the field, which is affected by soil moisture, plant shape, and the farm-specific microclimate. Our model is act as a calibration layer. It takes the weather forecast and corrects it to match what our on-field sensor actually reads. To answer this, we need to understand one key concept, GDD. GDD stands for Growing Degree Days, a measure of heat accumulation used to predict plant development stages such as maturity and harvest dates. The formula: each day we clip the hourly temperature to between 10 and 30 degrees Celsius. Take the average, subtract base temperature of 10, the minimum of corn growth, and take the maximum of that result and zero. We then sum daily GDD values into a cumulative total. Corn development follows a series of vegetative feed stages all the way to harvest. Each stage is a biological checkpoint when the cumulative GDD crosses the threshold for a particular stage. It signals that the corn has been progressed. Our goal is to predict when those thresholds will be crossed using forecast temperature data. Our primary data come from a grid by IoT board on a real farm, collecting two temperature readings, soil moisture, and light intensity. We also manually recorded each time the corn reached a new growth state. Our secondary data come from OpenMeteor, a weather API. We pull hourly temperature and humidity forecasts across 7 previous day horizons, giving us 7 different forecast versions for each timestamp, from 1 day ahead to 7 days ahead. Our dataset is generally complex. It is time series data that changes over time, comes from multiple sensors with different quality, has missing values from both downtime, follows 7-day horizons forecast structure, and arrives at a different time interval. We will 4-phase pipeline. Phase 1 EDA. We clean and export sensor data, select the best temperature sensor. Phase 2 Pre-processing. This phase we reshare weather data, merge datasets, and engineer features. Next, modeling. We train and compare 4 model combinations, rich and XGBoost, each on actual and residual targets average using hourly MAE, RMSE, R-squared, and selects the best performer for forecasting temperature. Finally, phase 4, growth validation. We convert predicted temperature into GDD and validate against the real growth log. Our sensor dataset has 10,408 records from a single farm location in Bangkok, covering soil moisture, light intensity, temperature, humidity, and the calibrated temperature TempI2C. Importantly, all selected columns have 0 missing values in the raw data. We can conclude that the sensors themselves were reliable, only the board has occasional downtime. We had 2 temperature sensors and needed to pick one. The raw sensor temperature showed a flat plateau at night, while temperature I2C showed a smooth realistic diurnal curve throughout the day and night. The value distribution confirmed this. Raw data's temperature produced integer-like spikes, while temp I2C gave a continuous distribution. Therefore, we selected temp I2C as our temperature source. The OpenMeteor dataset has 1,272 hourly records from March 8 to April 29, with 7 forecast versions per timestamp, 1 per horizon. Horizon 1 is yesterday's forecast, while Horizon 7 is what made 7 days ago. This structure lets us study how accuracy changes as lead times increase. Next, our growth dataset. It was manually collected by us. The dataset tracks progressions from early stages on March 16 to later vegetation stages on 7 April. This log is what we use to validate our GDD-based predictions. This chart shows GDD required to move between each state. There is real variation. V1 to V2 need 105 GDD, while V2 to V7 needed only 52. The average is about 79 GDD per stage. For the preprocessing part, first step we perform is binning. The raw sensor logs read every 5 minutes, but since OpenMeteor provides hourly data, we need to align both at the same resolution. We bin our sensor reading into hourly intervals by computing the mean temperature within each hour. The result is a clean hourly time series shown here. After binning, some hours had no readings due to board downtime. How we handle it is, we apply two strategies. Short gaps of 3 hours or less were filled using the median temperature of the same hour from a plus or minus 3-day window. We used median to avoid anomalous days distorting the imputed value. Longer gaps were dropped entirely since filling a large consecutive block would introduce too much uncertainty. Now that both datasets are at hourly resolution, we join them using an inner join on timestamp. Since the OpenMeteor data was reshaped to long format, with 7 rows per timestamp and 1 for each forecast horizon, the merged result has 6,155 rows.
Next pre-processing step is creating a residual column. A residual is a forecast error between forecast temperature and field temperature. And why do we need it? Simply, residual target tests whether learning the forecast error is easier than predicting temperature from the scratch. Next is cyclic encoding. We encode hour of day as cyclic feature using sine and cos, and it can help machine learning to understand cycle, and it preserves time of the day continuity. For an example, on hour 23 and hour 0 are adjacent, not opposite at all. Last but not least is feature scaling, where we scale forecast temperature, forecast humidity, hour sign, and hour cost, since it prevents features with large magnitudes from dominating the regularization penalty. Move on to test and train splitting, where we split into 80 and 20, 20 for testing and 80% for training. Here is a quick look into our dataset for training. Let's move on to another topic about analytic technique. We built 4 different models to compare them and find out which one will yield the most accurate result, where we try to compare between targets and models. For a target, we compare between predicting actual temperature versus predicting residual, or aka forecast error. For model, we will compare between ridge regression and XGBoost, which is gradient boosted decision trees. For model design decisions, there are not much big difference between using two models here, but the most different part would be about pre-processing, as regression will require feature scaling, as it will penalize large coefficients, so feature must be on the same scale, while XGBoost use tree-based splits. That means it only looks for at whatever one value is greater or less than a threshold. Next is model performance evaluation, where we compare all of the four models in three different metrics, including mean absolute error, root mean square error, and R square. And surprisingly, XGBoost, which is predicting the residual, achieved the best result across three metrics, where XGBoost achieved staggering zero point 0.5 Celsius difference from the actual field temperature and 0.655 Celsius difference for root mean square and about zero point 0.9 for R squared. And here is model overfitting comparison where we compare three metrics in training and testing. And we have found that XGBoost has more chance to overfit due to error gap in training and testing. And next evaluation is where we plot three metrics on each metric on each day ahead. And the result is pretty clear that XGBoost wins here. But honestly, why this model wins? We have further evaluation and exploration into it. And the results say that the model predicts the ratio between open material and field temperature is mainly driven by humidity. This is because evapotranspiration, and we have also found another clue about cyclic encoding, which is has some slight effect on the model accuracy. And we have also ran some feature ablation study where we try to subtract some pre-processing technique and some feature from the model, and the model was retrained four times, and the result is pretty clear that what we have built so far is the best, and the future is not overfitting at all. And here is the recap why this model wins and why this feature wins. First thing first, crops don't grow linearly. There are multiple nonlinear factors that we need to capture, and XGBoost wins here. Next is residual approach help model to only learn the difference and correct it. Lastly, residual target also reduce overfitting, and here is the evidence that we have provided. Let's move on to another topic about forecasting result, and here is the graph about how far off was the model in predicting dates. This shows how accurate the state prediction model was for each state. For example, if corn actually reached new state today, but the model predicts it will reach in 2 more days, that would mean 2 days error. And the graph shows that the model predict about 1 day errors. Here is also forecasting result into 7 days. And here is final output chart where we plot everything together, including the GDD and historical sensors, as well as the forecasting result. And it predicts that the crop will reach V7 stage around April 23rd and V8 stage around April 28th. For possible application for farmers, they can predict harvest date week in advance to plan labor and logistics. Get early warning if temperature anomalies will delay a growth stage. Replace manual daily observation with automate state tracking. And for agricultural businesses, they can schedule crop collection and transport more precisely, forecast supply volume and timing for buyer contracts. This can also be used for option pricing as well. Scale the pipeline across multiple farms by deploying the same sensor setup. For researchers, template for other crops that also use TDD-based cohort models like rice or sugarcane. It is also a baseline for testing more advanced models as more seasonal data become more available. Here is our reference to thank you for the presentation.